Hello, Math 200 students. We're on section 3.4, the last section in chapter 3, additional topics in probability and counting. This section is going to be a lot about permutations and combinations. All right, so permutations is how many ways can I arrange things in different orders. So it's like if I have 10 things and they're all distinguishable things, how many ways can I line those things up, first, second, third, fourth, all the way to 10th? Or it could be maybe I have 10 things and I want to just pick the best 3. How many ways can I pick just the best 3, first, second, and third out of 10? That's also a permutation. Combinations are actually when the arrangement or order does not matter. How many ways can I just take 3 things out of 10 and they don't have to be lined up first, second, and third? They're just taking any 3 things as 3 non-distinguishable things. So like taking 3 people and making a club out of those 3 people instead of making them be first, second, and third place or something. All right. So an ordering of n objects is called a permutation. A permutation is an ordered arrangement of objects. The number of different permutations of n distinct objects is n factorial. All right, let's figure out why that is. If I have 5 things, then there's 5 things. How many ways can I take those 5 different things and put them in some sort of an arrangement? Well, how many choices do I have for the first thing? I have 5 choices. But then that thing is gone. So then how many choices do I have for the next thing? I have 4. Then for the next 3, and then 2, and then 1. So that's 5 times 4 times 3 times 2 times 1. Well, that's the definition of 5 factorial. If you have n factorial, that means you're doing n times 1 less than n minus 1, times 2 less than n minus 2, times n minus 3, all the way down to 1. Okay? So that's how we can take any number of things. If you take n things, how many ways can you do a permutation, meaning an arrangement of n things? It would be n factorial. Okay, so that's just what this is teaching. Notice it said that a special case is 0 factorial. All right, 0 factorial is just going to be defined as 1. Okay. So here's an example. The objective of a 9x9 Sudoku number puzzle is to fill the grid so that each row, each column, and each 3x3 grid contain the digits 1 to 9. How many different ways can the first row of a blank 9x9 Sudoku grid be filled? So just the first row of a Sudoku puzzle, where all the numbers in a row have to be the numbers 1 to 9. Okay, so then you can see that the answer here, well, how many choices do we have for the first spot? We got 9 choices, but then that number's taken. So then we got 8 choices, and 7 choices, and 6, all the way down to 1. So the number of permutations for that row is 9 factorial, which is 362,880. That's how many different ways the first row can be filled. All right. Now, like I said before, you may not want to choose, you may want to choose just some of the objects in a group and put them in order instead of taking all the objects. So that's called a permutation of n objects taken r at a time. Number of permutations of n distinct objects taken r at a time is defined as npr. Little n, little r, those are subscripts, and the p is a normal p. And that is going to be n factorial over n minus r factorial. All right, let me show you an example of that. Let's say we have 10 objects. We want to take 3 things and arrange them. Okay. How many choices? We're only arranging 3 things. How many choices do we have for the first thing? 10. for the second thing, 9 for the third thing, 8. So it's 10 times 9 times 8. Well, 10p3 is 10 factorial over 10 minus 3. I wish it wouldn't have done that. 10 minus 3 factorial, which is 10 factorial over 7 factorial. And let me show you why that's the same thing as this. It's 10 times 9 times 8 times 7 times 6 all the way down to 1, right? Okay. Over what? 7, 6, 5, 4, 3, 2, 1. Well, all that crosses out with all that. Another way you could say that is 10 times 9 times 8 times 7 factorial. You can stop that factorial anywhere you want because 7 factorial is 7, 6, 5, 4, 3, 2, 1 over 7 factorial. And 7 factorial cancels with 7 factorial. Either way, what do you end up with? 10 times 9 times 8. Like I said before. So if you've got n things taken r at a time, when order matters, that is npr, which is n factorial over n minus r factorial. Now let me show you how you can do a couple of these things in your calculator. Let me get my calculator pulled up here. TI, where are you? There you are. It's coming up. Okay. If we wanted to do 10p3, we could just say 10, then hit math, click over to where it says prob, that's probability. And on the probability menu, you see you have these, the NPR, the NCR, and the factorial symbol are going to come in very handy in this unit. So we want to do option 2, the NPR. Okay. And so we got 10p and then 3. 10p3, and it tells me the answer, 720. That's 10 times 9 times 8. Let's say we just wanted to do 10 factorial. It's just going to be 10, math, click over to prob, option 4. Maybe too big. No, it fits. 3,628,800. Okay. So let's keep on trucking. Example 2, finding NPR. Find the number of ways of forming 4-digit codes in which no digit is repeated. Okay, that's going to be, you think about it like this, 1, 2, 3, 4, 10 times 9 times 8 times 7. Or we could say 10p4. That's a 4-digit code taken out of the 10 single digits 0 through 9. Or we could just do in the calculator 10 math, click over to prob, option 4, not option 4, sorry. 10 math, click over to prob, option 2 NPR 4, and that'll give us the answer, 5,040. Different ways you can get that. Okay. 43 race cars started the 2013 Daytona 500. How many ways can the cars finish first, second, and third? All right, I'm not even going to go over there and do it. I'm just going to show you from the solution they've got written here because it's already just like we've been doing. 43 things, you want to take 3 of them and put them in order. That's 43p3. So there's 74,000 something different ways that you can have a first, second, and third place finisher in the Daytona 500. All right, you may want to order a group of n objects in which some of the objects are just exactly alike. For instance, consider the group of letters A, B, B, C. This group has 4 A's, 2 B's, and 1 C. How many ways can you order such a group? Using the formula for NPR, you might conclude that there are 7P7 or 7 factorial possible orders. So the reason they're saying 7P7 is because you got 7 things and you're ordering all 7 things. So that's 7P7, which turns out to just be 7 factorial. However, because some objects are the same, not all of these permutations are distinguishable. In other words, if you swapped 2 of these A's up here at the beginning, all right, if you swap 2 of these A's, you wouldn't even know the difference. You wouldn't be able to tell that that's something different at all. They're indistinguishable. So how many different distinguishable permutations are possible? The answer can be found using the formula for distinguishable permutations. Here is the formula for distinguishable permutations. The number of distinguishable permutations of n objects where n1 are of one type, n2 are of another type, and so on, is n factorial over n1 factorial, n2 factorial, n3 factorial, all the way down. All right? Using the formula for distinguishable permutations, you can determine that the number of distinguishable permutations of those letters given up here, it would be there's 7 different letters, so there's 7 total things, 7 factorial, over there's 4 A's, so over 4 factorial, there's 2 B's, so 2 factorial is also on the bottom, and 1 C, so 1 factorial is also on the bottom. So you can see that right here, 7 factorial over 4 factorial, 2 factorial, 1 factorial, which reduces to all that, it's just 105. All right. So here's another example. Finding the number of distinguishable permutations. A building contractor is planning to develop a subdivision. The subdivision is to consist of 6 one-story houses, 4 two-story houses, 2 split-level houses. So I'm assuming that the 6 one-story houses are all alike, the 4 two-story houses are all alike, and the 2 split-level houses are both alike. In how many different distinguishable ways can the houses be arranged? All right, let me show you how to do that. There were how many total houses was it? Let's look back. How many total is it? Well, there's 6 and 4 and 2. So altogether, the total number of houses is going to be 12. So it's going to be 12 factorial over 6 factorial, 4 factorial, 2 factorial. So in my calculator, I would just have to type that in. 12 factorial divided by, and then I'd have to open a parentheses to put lots of things in the denominator down here. 6 factorial, 4 factorial, 2 factorial. Notice again, I have the 6, 4, and 2 factorial all in parentheses after the division symbol, so that the calculator knows I'm dividing by all 3 of these, not just dividing by the first one. Otherwise, it would just divide by the 6 factorial and then multiply by the 4 and the 2 factorial. And that's the answer we get. Okay. Keeping on going. Next topic is combinations. Remember what I said about combinations? Combinations is where the order does not matter. Okay? Permutations, the order does matter. Combinations, the order does not matter. All right, a state park manages 5 beaches labeled A, B, C, D, and E. Due to budget constraints, new restrooms will be built at only 3 beaches. There are 10 ways for the state to select the 3 beaches. And then it lists them all out. A, B, C, A, B, D, A, B, E, and so on. It just lists them all out. So how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 different ways that you could take 3 beaches out of those 5 to do the renovations. All right, or to do the restrooms. In each selection, order does not matter. If you do ABC beach, that's the same thing as doing BAC beach. It doesn't matter that because you're doing the same beaches regardless of if you say I'm doing ABC or doing BAC. The number of ways to choose R objects taken from N objects without regard to order is called the number of combinations of N objects taken R at a time. The number of combinations of R objects selected from a group of N objects without regard to order is NCR, which is n factorial over n minus r factorial. That's the same as permutations, but with this one extra factor of r factorial on the bottom. That is what allows that extra r factorial on the bottom allows you to remove some of these extra arrangements that shouldn't count as separate things if the order does not matter. So if ABC and BAC are the same thing, they shouldn't be counted twice. And so that extra r factorial on the bottom is what takes care of that. Okay, let's look at example 5. A state department of transportation plans to develop a new section of interstate highway and receives 16 bids for the project. The state plans to hire 4 of the bidding companies. How many different combinations of 4 companies can be selected from the 16 bidding companies? All right, that's going to be 16C4, because it doesn't matter what order the company is selected. All 4 of them are going to get these bids. It doesn't matter if they're selected first or fourth, they're going to get the bid. All right, so let me go to here. It's going to be 16C4, not P4, which is 16 factorial over 16 minus 4 factorial, 4 factorial. In other words, 16 factorial over 12 factorial, 4 factorial. All right, and we can do that also in our calculator pretty easily. We say 16, go to math, click over to prob, and there's an NCR option with option 3. So I'm going to click option 3, 4. 16C4 is 1,820. Okay, keeping on trucking. There's a table right here that summarizes the applications of counting principles. The normal fundamental counting principle. If one event can occur in m ways and a second event can occur in n ways, then the way they can occur together is m times n. Permutations is a special case of that, because it's like I could use this digit and then this digit and then this digit, so it's still kind of the same thing as the fundamental counting principle. All right, but that table there summarizes the counting principle with permutations and combinations. All right, along with distinguishable permutations. Example 6. A student advisory board consists of 17 members. 3 members serve as the board's chair, secretary, and webmaster. Each member is equally likely to serve in any of the positions. What is the probability of selecting at random the 3 members who currently hold the 3 positions? When you encounter these kinds of problems, the first thing you need to decide is, does the order matter? What do you think in this problem? Does the order matter? The order does matter in this problem, because you're taking 3 people and you're giving them 3 different titles, 3 different positions: a chair, a secretary, and a webmaster. If you were taking 3 people and just making a committee or a team out of them with no regard to who is taking a different position than someone else, then it wouldn't matter and use combinations. But in this case, since the order does matter, we're going to use what? Permutations. So we're just going to do 17P3 because we're picking 3 people. 17P3 gives me 4,080 when I put it in my calculator. So, but the probability is actually, so the 4,080 is just how many ways I can pick 3 people and put them in 3 positions. But it says, the question was, what is the probability of getting the 3 members exactly who currently hold the position? It's there's only one way to get those exact 3 people to hold those exact 3 positions. So it's 1 out of 4,080, which is about 0.0002 or 0.02%. Probably a very low probability. Okay. Find the probability of being dealt 5 diamonds from a standard deck of 52 playing cards. By the way, so this is getting into poker, which I really enjoy. I really enjoy thinking about poker hands and playing poker, I don't think anybody should gamble as far as like in a way that could possibly hurt their financial outlook. But you know, if you're just like gambling for M&Ms or something, that's pretty cool. I enjoy that. So there's 52 cards. Okay, there are 13 of each suit. Sorry, yeah, of each suit. There are 4 suits. All right, we can say 13 ranks in each suit, and there are 4 suits. All right, you may be real familiar with cards, in which case this will be easy for you to think about. If you're not very familiar with cards, this will be harder for you to think about. But you got to go back and look at the video where I showed the different cards that are in a deck of cards. In poker, you get 5 cards. You get dealt 5 cards. If you get 5 diamonds or 5 hearts or 5 of any different suit, that's called a flush. Flush is getting 5 of the same suit. Okay? So if we're talking about the probability of getting 5 diamonds, that's going to equal. All right. How many diamonds are there? There are 13. And I'm getting how many of them? I'm getting 5. Does the order matter? No, the order does not matter. I'm just getting any 5 of the diamonds to get the same suit. So that means how many ways can I do that? 13C5. 13C5. That's the numerator. That's how many ways I can successfully get 5 diamonds. Okay, the denominator is the entire number of possibilities of getting any 5 cards at all in your hand. So how many ways can I get any 5 cards from the 52? How many cards are there? There's 52. How many do I need to get? 5. And the order does not matter. Okay, so 13C5 over 52C5. And let's see what that probability is. Okay, 13 NCR 5 divided by, I gotta click to the right to get out of that subscript. Now divided by 52 C NCR 5. Okay, 4.95 blah blah E negative 4. That capital E negative 4 is the calculator's shorthand of doing scientific notation. It means times 10 to the negative 4th. So in other words, if you want to, it's 4.95 times 10 to the negative 4th, which means I'm moving the decimal point 4 places to the left. So let me do that here. 4.95 E negative 4, that's the same thing as 4.95 times 10 to the negative 4, which means I move the decimal point 4 places to the left, which means I've got a decimal point and then 3 zeros, and then the 495. So that's the probability of being dealt a flush. All right, now it doesn't take into account that you can trade cards in for other cards that I know, but this is the probability of being dealt, not being dealt a flush, but of being dealt 5 diamonds. The probability of being dealt a flush is it'd be higher than that, because you'd have to take into account that you could get 5 diamonds or 5 clubs or 5 hearts or 5 spades. But that's the probability of being dealt 5 diamonds. Okay? About 0.05%. 0.05, that's very low. Which is why a flush is worth a lot in poker. Let's do some more of that, because I really enjoy that kind of a thing. What in the world just happened? Okay, let's do the probability of getting a flush of any kind, not just diamonds. Okay, probability of getting a flush of any kind. First, I need to choose a suit. How many suits do I have to choose from? I have 4 suits to choose from, and I just need to get one of them. So 4 choose 1 times. Now how many cards are in that suit? 13. And how many do I need to get? I need to get 5 of those 13. So this is choosing a suit. Choose suit. This is choosing 5 cards from that suit. Choose 5 cards from that suit. Divided by, so this is the number of successful ways on top. On bottom, it's the number of ways to get any hand in poker. And what's that again? 52 choose 5. So 52 choose 5 is always going to be the denominator if I'm talking about 5-card poker. So let's see what that is. Okay, parentheses, 4 choose 1 times 13 choose 5. Get out of that, close my parentheses. Divided by 52 choose 5. And it's a little, it's a good bit higher. It's 0.00198. So I'm gonna say 0.002 then. Almost 0.002. So about 0.2%, which was a good bit higher than 0.05%. Okay, let's do some more of that. What's the probability of getting 2 of a kind? I should say this. What's the probability of getting at least 2 of a kind? That means I could get 2 or 3 or 4 of a kind, and this is the probability of getting at least 2. Well, 2 of a kind, that means 2 of same rank. Okay, not of the same, not the same suit, but the same rank. Okay, 13 ranks. Okay, and 4 in each rank. So like, what's the probability that I get 2 kings or 2 jacks or 2 5s? First, I need to choose a rank. I can choose from 13 different ranks, and I just need to get one of them. That chooses a rank. Choose rank. Next, I need to choose 2 cards from that rank. How many cards are in that rank? There are 4. And how many do I need? I need 2 of them. Next, but that only gets me 2 cards. I still got to get 3 more cards. So I need to choose any 3 other cards. How many other cards are now left in the deck after I've taken the 2 that I needed just now? That means there's 50 left in the deck. And I get to choose any 3 of those. So there's my numerator. That's how many ways I can choose any hand of 5 cards that has at least 2 of the same rank in it. And that's divided by what? Divided by the number of ways I can get any hand in poker, which is 52 cards, and I'm choosing any 5. Let's see what that probability is. Okay. 13 choose 1 times 4 choose 2 times 50 choose 3 divided by 52. Yeah. 52 choose 5. 0.5888 is the probability there, 0.588. So about almost 59%. So you got pretty good odds of being dealt a hand that has at least two of a kind in it. So if you've got two of a kind, that's not a very great hand. There could be other people that have something better. All right, let's do the probability of three of a kind. Okay, let's see. Maybe you could do this on your own by now. First, we need to choose a rank. 13, choose one. 13 ranks, I choose one of those ranks. How many cards are in that rank? 4. And I need to get how many? I need to get 3 of those. I need to get 3 out of those 4. And then that gives me 3 cards. How many cards do I need left to fill out my hand if I've got to get 5 cards? I've got to get 2 more cards, because that's 3. I got to get 2 more to make 5. How many cards are left in the deck after I pick those 3? There's 49 cards left in the deck, and I've got to get 2 of those to fill out my hand, and that's over 52. Choose 5. Now, I won't go to the calculator and do that. You can do that yourself. Try to do the probability of 4 of a kind. Try to do that yourself. 13, choose one rank. 4 in that rank, choose all 4 of those. 4, choose 4. And then it gets me 4 cards, and I need 1 more card to fill out my hand. There's 48 cards left in the deck, and I just need to choose 1 of them. Divided by 52, choose 5. See what that probability is. All right, I won't do that in my calculator. 1 more. What's the probability of a full house? Full house means 3 of one rank and 2 of another rank. Now, the probabilities here are going to tell you what hands are more valuable than other hands, because the ones that have a lower probability are more rare, and therefore they are considered to be better hands. So if you want to know which one wins, 4 of a kind or a full house, just do this probability. Whichever one is lower, that's the one that wins. So a full house. First, I need to do 13 ranks, and I need to choose. Let me think about that for a second. 13, choose 2. That's 2 ranks. I'm picking 2 ranks out of the 13 to get my 3 of a kind and my 2 of a kind. Okay, so and then that's gonna be times. After I do that, I've got 4 cards from one of the ranks, and I need to pick 3. And I've got 4 cards from another rank, and I need to pick 2. And that gets me all 5 cards. So I don't need any other cards in my hand, so I'm done in the numerator. And that's divided by 52, choose 5. All right, that's a pretty good introduction to doing the probability of a game like poker, which gives you a good feel for how to do probability in general, I think. Here's an example that uses the same concepts as what I just showed you in the probability of a card game, but this is probably more important. Stuff like in the real world of manufacturing and safety and stuff like that. A food manufacturer is analyzing a sample of 400 corn kernels for the presence of a toxin. In this sample, 3 kernels have a dangerously high level of the toxin. 4 kernels are randomly selected from the sample. What is the probability that exactly 1 kernel contains a dangerously high level of the toxin? All right, I wrote the information down here. We got 400 total kernels. 3 out of those 400 are toxic. We're taking 4 kernels for a sample. What is the probability that exactly 1 out of the 4 in our sample is one of the toxic ones? All right, so there are 3 toxic ones. I just need 1 of them for my for this to happen, for there to be exactly 1 of the 4 to be toxic. All right, but I've got to get 4. I need 3 more to fill out my sample. So if I've already picked one, how many are left to pick on? Okay, first I'd want to say 399. I'm going to erase this. I'd want to say 399, choose 3. But that would be if I wanted to pick at least one, because then I could see one of these other ones could also be toxic. So the way that I can say I just need to get exactly one is to say I'm not picking out of 399. There are 397 of those that are non-toxic, because 3 were toxic, 397 are not. So I need to pick from those to fill out the rest of my sample, and I'm getting 3 more to fill out my sample because I've already got 1 there. That's going to be divided by the total number of ways to get a sample, any sample of 4 from the 400. So that's 400, choose 4. So that should get my probability for that example. And that is exactly what they did here. And the probability is 0.03 to get exactly one of those. All right, I think that, I just wanted to, before we end this section, I wanted to maybe again get a feel for when do you use combinations, when do you use permutations. Okay, so I'm just going to think of some examples and you tell me which one would work. Okay, I have 25 students. I want to get a committee of 5 students from those 20. Should I use combinations or permutations to figure out how many ways that can happen? That would be combinations, because I'm getting a committee of 5 students, so the order of those students doesn't matter. They're going to be the same committee no matter the order that they were picked. What if I wanted to get 3 students from a class of 20 and make them be the class president, vice president, and secretary? I'm going to use permutations because the order matters, because I'm putting them in different spots, different positions. What if I wanted to get a pizza and there were 10 toppings and I wanted to get 3 of those toppings? How many ways could that happen? I'm going to use combinations because I'm picking 3 toppings and the order of the toppings does not matter. Unless you're a really, really picky pizza person, you don't care which topping they put on first and which topping they put on second or third. So I'd use combinations. Let me think of another example. Or what if there was a 10-question test and you needed to get 7 of them right to pass the test? How many ways could you get 7 problems right? You'd use combinations because it doesn't matter what order the problems are in or which 7 problems it is. You just need to get 7 problems right, so you'd use combinations. That's the last example for that section. So good luck on that assignment, and I'll see you again in Chapter 4.